Okay, next we define the continuity of a function. So here's the definition. Let's say f is a function that is defined on an interval I, and so assume this point A is in this interval. Okay. Then we say f of x is continuous at A. Okay, continuous at A. So this means the limit of f of x as x approaches A is equal to f of A. Okay, so this is the definition of continuity at a certain point. Okay, and next, similarly, we say f of x is a continuous function. Continuous function. And this means f of x is continuous at all x in the interval. Okay. So first we define the continuity at a certain point, at each point, right? And if f of x is continuous at every point within the domain, then we say that function f is continuous. It's a continuous function. Okay? So let's rephrase the same thing using epsilon and delta. Okay, first continuity at one point. So that in this case, f is continuous at A. So this means this condition. For all epsilon that is positive, and there exists, there exists some delta that is positive and real, such that for all x within I, x minus a, the difference between x and a is greater than 0 and less than delta implies f of x, the difference between f of x and f of a is less than epsilon. Okay, so this is continuity at point A. Next, if we want to say f is continuous, simply continuous, that means continuous at every point in the domain. So f of x is continuous. Then using this epsilon-delta argument, we say for all a in the interval, this holds. Okay, so we can just write like this. Okay, so this is less than epsilon. So for every point in the interval, for all epsilon, there is a delta, positive and real, such that for all x within the interval, if the difference between x and a is less than delta, then it means the difference between the values of f of x and f of a is less than epsilon. But please note that this delta may depend both on epsilon and epsilon and a. Sorry, because a comes here and epsilon comes here, so this delta may depend on these values. Okay. If this delta does not depend on a, then it's a very strict condition for continuity. It's called uniform continuity, but we don't discuss this here. Next, if we want to say f is continuous, simply continuous, that means continuous at every point in the domain. So f of x is continuous. Then using this epsilon-delta argument, we say for all a in the interval, this holds. Okay, so we can just write like this. Okay. Okay, so this is less than epsilon. So for every point in the interval, for all epsilon, there is a delta, positive and real, such that for all x within the interval, if the difference between x and a is less than delta, then it means the difference between the values of f of x and f of a is less than epsilon. But please note that this delta may depend both on epsilon and epsilon and a. Sorry, because a comes here and epsilon comes here, so this delta may depend on these values. Okay. If this delta does not depend on a, then it's a very strict condition for continuity. It's called uniform continuity, but we don't discuss this here. Let's see a few examples. Let's see. First, let us define a function f from real to real by this. F of x is equal to 0 if x is negative, and it is 1 otherwise. Okay, so this the graph of this function looks like this. If this is x, if this is f of x, then it is 0 here, and here this is not included, and 1 from here, and this value is included here. Okay, so if we take this limit f of x as x approaches 0, then there is no limit, right? So if you approach from negative side, it converges to 0. So the left limit is 0, but the right limit, if you approach from here, it is 1. So the limit at 0 doesn't exist. Therefore, this function is not continuous at x equal to 0. Okay, so not continuous at x equal to 0. Okay. And another example. Let's define a function by f of x equal to modulo x if x is not 0. and -1 if x is 0. So this function looks like this. Okay. So it's like this on the positive side, and it looks like this on the negative side. But this point is not included. Okay, at x equal to 0, it takes the value of -1 here. Okay, so if you take the limit of this function as x approaches 0, the right limit is 0 and the left limit is also 0. So the limit exists. So the limit is 0. But this is not equal to the value of f of 0, which is -1. Therefore, this function is not continuous, although it has a limit at x equal to 0. Here's some remark about a function that is defined on a closed interval. For example, f of x is defined on, suppose, on a closed interval between a and b. And when we say f of x is continuous at a, what do you mean? There's no anything left of a, right? I mean, because that's the leftmost element of this interval, so you cannot define the limit of this function at a or at b. Now we can only define the right limit for a at a and the left limit at b. So if this limit, so the right limit, x approaches to a from the right, if this is equal to f of a, then we say f of x is continuous at a. And similarly, limit of f of x approaches b from the left. If this is equal to f of b, then we say this function is continuous at b. This is a special case. The next theorem should be trivial. Okay, so let's see. Theorem. Let f and g be g of x be functions continuous at x equal to a. Okay, both are continuous at a. Then we have the following. Okay, first, the linear combination of these functions is also continuous at a. Is continuous, let's abbreviate, at a. And so is this. And so is this. Given that g of a is not 0. Okay. So this should be trivial because we have already proved a very similar theorem for general limits. In this case, those limits happen to be the values of these functions at x equal to a. So nothing special. Okay, so I just skip the proof. And by this theorem, you can see that all polynomial functions are continuous at every point on the real axis. And the next theorem is also trivial. It's about composition of functions. So let's see. Let's say f of x is a function on defined on an interval I, and a belongs to I, and the value of f of x at a is b, and also g of x is defined on some interval, let's say j, and b, the point b belongs to this interval j. And suppose they are continuous. Okay, f of x is continuous at a, and g of x is continuous at x equal to b. Okay, so suppose all these conditions are met, then the composition g after f is continuous at x equal to a. And this is also a special case of the theorem we have proved before for for general limits of function compositions, right? In this case, those limits happen to be these values and the g of b. So the limit of this as x approaches b is g of b, and the limit of f of x as x approaches a is b. So in this case, this just reduces to the previous theorem. So again, I skip the proof. The next theorem is actually very important, but I do not give the proof just because it's not too difficult, but it's quite involved, so I'll just skip it. It takes too much time. So it's called intermediate value theorem. Okay, so let f of x be a function on a closed interval, be a continuous function on a closed interval. Okay, so this is important. It's closed. And so we are just saying it's a continuous function, so this function is continuous at every point within this interval. Okay, and such that f of a is not equal to f of b. So their values at the endpoints are different. Okay, and then for any L, some value between okay, let's see, between these values f of it's okay, for all L between f of a and f of b. So we are not specifying which is larger and which is smaller, but any value between them. So for all values between f of a and f of b, there exists certain values, see, within this interval such that f of c is equal to L. Okay, so I don't give the proof, but we should understand what this means. Okay, it's quite intuitive. Suppose we have a function defined on a closed interval. Okay, so this is A, this is B. Okay, so we have a function. And the values at B is different from the value at B is different from the value at A. Okay, so let's say in this case f of A happens to be less than f of B. Anyway, so for all L between f of A and f of B means we pick any value between this and this. Okay, so any value. So let's pick this one. Let's pick this one, L. Okay, for this L, there is some C such that f of C is equal to this L. Okay, so this means if we draw this horizontal line, then there is some point that crosses with this horizontal line crosses with this graph of f. So at this point, that's the value of C we want. Okay. So that's what this means. So this can, be said for any values. So if you pick this one, maybe it crosses here. So the value of C should be here. If you pick this one, if you pick somewhere here, then it should be somewhere closer to B, and this should be the value of C. Okay, so this is a very simple but quite powerful theorem. And the next theorem is also important, but we give without proof, and that's called the extreme value theorem. Okay, again, f of x is defined on a closed interval. Okay, so closed is important. And on this interval, and it's a continuous function. Okay, then f of x has a maximum value and a minimum value at least once. Okay, so what does this mean? So if a function is defined on a closed interval a and b, and it is continuous, so continuous at every point in this interval. Suppose, let's see. So this function always has a maximum and a minimum. So in this case, the maximum is here and the minimum is here, right? And let's see another example. So very simple example like this. Okay, so this is A, this is B. In this case, minimum is here exactly at A, and the maximum is exactly at B. Okay, so this is possible because this interval is closed. Okay, what happens if it is not closed interval? Suppose this is open interval. In this case, the point here is not included, so the endpoints are not included in the domain. So this is, so this function has a limit at a, which is some value here, but that is not f of a. Okay, f of a is not defined here. Therefore, this function does not have the minimum. And similarly, if the domain does not include this endpoint b, this function has a limit at x equal to b, but it doesn't. F of b is undefined. F of b is undefined, so this function does not have a maximum. And let's see another example. For example, let's see, if we define f of x as 1 over 1 minus x squared, defined on an open interval from -1 to +1. Okay, so this function looks like this. So let's say this is 1, a -1, 1, 2, 3, 4, 1, 2, 3, 4. So this is +1. So this function looks like this. Okay, it diverges to infinity, positive infinity, as it gets closer to either positive or -1. And this is +1. And this point and this point are not included in the domain. So it does not have a maximum. Now, this is very big numbers at near endpoints, but they are not maximum. Okay, from now I'll explain some of the elementary functions. First of which are algebraic functions. So, for example, first of all, the easiest one is the polynomial. Okay, something like this: a n x to the power of n, a n minus 1, x to the power of n minus 1, and so on, and a1x plus a0, where all these coefficients a n, a minus 1, and so on, they are real numbers. Just write ai are real numbers. I is 0, 1, up to n. And these polynomial functions are defined for all real numbers. So the domain is the entire real numbers, entire set of real numbers, and they are continuous. Okay, so those are polynomials. Okay. Polynomial functions. And let's say if g of x and h of x are polynomials, such that h of x is never 0, then we can define another function by the ratio between these two, g of x over h of x. And this type of function is called rational function. Just like rational numbers. And in some cases, at some point, this hx may be 0. So in that case, those points are excluded from the domain of definition of this function. Okay, and also, as long as h of x is not 0, this function f of x is continuous. Okay, so maybe we should write defined on this domain. Okay. And if h of x happens to be a constant 1, constant 1 is also a polynomial, right? So in this case, all an minus 1 and so on, they are all 0 up to a1, but a0 is just 1. So this is a polynomial function. So in this case, f of x is just a polynomial function. So that means the set of all polynomial functions is included in the set of all rational functions. Okay. We can also define other functions algebraically. So algebraically. For example, f of x being square root of x. Okay, this is not a polynomial, obviously, and it is also not a rational function. It cannot be expressed as any ratio of polynomial functions. So this is not a rational function. But still, we have this equation, f of x squared minus x is equal to 0. So in a sense, this f of x can be defined algebraically using this equation. Okay, so this is a polynomial function, right? So in general, we can define algebraic function by the following. Okay, so f of x, let f of x be a continuous function. And continuous function is algebraic. So this means this. There exist some polynomials g0 of x, g1 of x, and up to gn of x. So these are polynomials such that this equation holds. Gn of x times f of x to the power of n plus g of n minus 1 x times f of x to the power of n minus 1 and so on, down to g1 of x times f of x and plus g0 of x is equal to 0. So if we can find n minus 1 functions, so this n can be any number. It can be just 1 or maybe 2 and so on. And such that this equation is satisfied somehow. Okay, then we say this f of x is defined algebraically, or it is a algebraic function. So we've already seen an example here. So in this case, f of x satisfies this function. So in this case, g1 of x is 1. It's a polynomial. And wait a minute, g0 of x is negative x. So this is a polynomial. So by using these two polynomials, we can satisfy this equation. Oh, actually, this is not g1, it's g2. Okay, and g1 should be 0. Okay. So by using these two or maybe three functions, f of x satisfies this equation. So we say this function, although it's not rational, it is defined algebraically. Next, we define the exponential functions. So let a be a positive real number. Okay, then the function defined by a to the power of x is called the exponential function. Exponential function with base a. Okay, this a is this a. Okay. In particular, when this a is equal to e, that is Napier's constant. Then we say this e to the power of x is the exponential function. And as you already know, I guess, if a is greater than 1, then a to the power of x is strictly increasing. It's monotone increasing. And if a is less than 1, a to the power of x is monotone decreasing. And when a is equal to 1, a to the power of x is just 1. So the graphs will look like this. This function is defined for entire real numbers. Okay, so this is x, and if a is greater than 1, it looks like this. And when x is 0, then a to the power of 0 is always 1. Okay, so a greater than 1. And when a is less than 1, then it looks like this. It's a monotone decreasing function that will converge to 0 when x goes to infinity. And when a is 1, then it's a constant. So, like this. In chapter 4, we actually introduced the exponential function as the inverse function of the logarithm, which was in turn defined in terms of an integral. But here, we define the exponential function like this, then define the logarithm as the inverse of the exponential function. Okay, but before that, we need to mention this important theorem, which we just give without proof. Okay. So that is so if f of x is a continuous. Actually, we used this theorem before already. Continuous and monotone, strictly monotone increasing. Monotone increasing. Okay. Then there exists the inverse of x. Okay, such and okay, there exists inverse of f of x that is also strictly monotone increasing. And an analogous theorem holds if the function is strictly monotone decreasing. In this case, the inverse function is also strictly monotone decreasing. Okay, actually we've used this theorem before when we derived the exponential function from logarithm. So here we didn't use any integral yet, and we just defined exponential function like this. But of course you should think about what this really means. Okay, it's easy to see what a to the power of n, where n is a natural number. So if what this means is easy to understand. This is just a is multiplied by itself n times, right? But when this exponent is not a natural number, what about negative integer? What about rational number? What about real numbers? Then it's not so trivial, but you should be careful. And please try to examine what this really means. Okay. So anyway, we define the exponential function, and the logarithm function is defined as the inverse function of the exponential function. So if f of x is a to the power of x, where a is positive, then the inverse of f of x is defined as the logarithm with base a. Okay, so this a is this a. Okay, so this is the inverse of this. And when a is Napier's constant, we just omit this a, and we say it's a natural logarithm. Now you know what algebraic functions are, and many functions can be defined as algebraic functions. But not all functions are algebraic, and those that are not algebraic, those functions are called transcendental functions. Wait a minute. Let me check the spelling. Transcendental. Dental functions. And those include exponential and logarithmic, and of course, trigonometric functions and so on. By the way, there is also the notion of transcendental numbers. Maybe you should check what this is. Now, there are algebraic numbers and transcendental numbers. And just like that, we have algebraic functions and transcendental functions. Now let's prove a few theorems regarding exponential and logarithms. We have the following limits. X approaches 0, log 1 plus x over x is 1. Okay, first prove this. So actually, to prove this, you need to first prove this holds. This should be equal to log 1 plus x to the power of 1 over x. Okay, I don't give the proof of this, but you should do it. In general, you have this. So let's see. For example, maybe I write a log x is equal to log of x to the power of a for any real number a. Okay. Anyway, once you know you admit this fact, it's easy to prove. Now this is limit x going to 0. This is 1 plus x 1 over x, and from a previous result, this limit, wait a minute, I should take log of this. Inside the log, this limit is is the Napier constant, Napier's constant. So this is basically the composition of this function and the logarithm. So we can conclude that this converges to this. But here, the base of this logarithm is e, so this is 1. Okay. And another result is, so 2, limit x approaches 0, e to the power of x minus 1 over x is 1. Okay, this is x. And this is easy once you substitute the variable by defining x equal to log of 1 plus t. Then this means 1 plus t is exponential of x, right? So this limit, the left-hand side is equal to limit. And also if x goes to 0, then then t is equal to exponential of x minus 1. So when x is 0, exponential of 0 is 1. So 1 minus 1 is 0. So when x goes to 0, then t goes to 0. So t to 0. And so exponential of 1 is, so the numerator becomes t, and x is equal to log of 1 minus t. And then we can use the previous result. Okay, so this. Okay, now this is log 1 plus x over x, but it's the reciprocal of that. So this is 1. And that's done. Now let's consider trigonometric functions. We already know sine x and cosine x and tangent x. Okay, for sine and cosine, x can be any real numbers. For tangent, we have to exclude some of the values. So in fact, x should be in this set. All real numbers except for this type of real numbers. So n plus 1/2 pi, where this n is an integer. Okay, so it's like half integers, multiple of pi are excluded. Okay, so these points are excluded because the definition of tangent x is this: cosine x over sine x over cosine x. So we want to exclude the points where cosine x becomes 0, and those are the points that happens. Okay, anyway, so that's not new. And we also know that these functions are periodic. So for sine x, we have sine x plus 2 pi n is the same as sine x for all n being integers. And same for cosine. Cosine x plus 2 pi n is the same as cosine x. And so they have the period of 2 pi n. And for tangent function, we have actually this pi n. So the period is pi. Tangent x. Okay, so that's not really new. And what's new is this: something involving a limit. So x goes to 0, sine x over x is equal to 1. Okay, at this point, we don't prove this, so you can just use this as a fact. Later, after we learn differentiation and something called L'Hopital's rule, we can prove this. Right now, you can just use this as a given fact. So let's see some examples. Okay. So consider this limit, 1 minus cosine x over x squared when x approaches 0. Wait a minute. Okay, so to consider this, let's see. Limit 1 cos x over x squared. So multiply both numerator and denominator by 1 plus cosine x. Okay, so this becomes limit and 1 minus cosine squared x and x squared 1 plus cosine x. But 1 minus cosine squared is sine squared. And we have x squared here and 1 plus cosine x. And we can now use this theorem. So this is square of sine x over x. Okay, so this sine x over x converges to 1, and when x goes to 0, cosine x approaches 1. So this limit should be 1 over 2. Next, we define inverse trigonometric functions, and as the name suggests, they are the inverses of trigonometric functions. However, if you consider, for example, sine function, it is a periodic function, so it looks like this. So it has something like this. So it has periods. So that means if you consider sine as a function from real numbers to real numbers, then it is not a bijection. So that means for example, this x and this x has the same value of sine x, right? So this is not injective. Therefore, we cannot define its inverse function. However, if we limit the range, the domain of definition of sine function from, for example, I mean there are multiple choices, but for example, if we limit the domain of sine from negative pi half to positive pi half, so within this region, then this function is a strictly monotone increasing function. Therefore, if we consider sine as a function from this interval, negative pi half to positive pi half, to this range, negative 1 to positive 1. So this is negative 1 and this is positive 1. Positive 1. So then this function is a bijection. Therefore, we can define its inverse. And that inverse is called arcsine. So this is a function from this domain, this interval, negative 1 to positive 1. And the range is negative pi half to positive pi half. Okay, so the inverse function of this function looks like this. So it's like we take the mirror image along this red line, so along this line. So I think it should look like, let's see. So negative 1, 2, 3, 4, 1, 2, 3, 4, positive 1. And when it's positive 1, it takes the value of positive pi half. And when it's negative 1, it takes the value of, negative pi half. So let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, somewhere here. So it should look like this. So this is the inverse function of the sine function, which is called arcsine. And in a similar manner, we can define the inverse of cosine by limiting the domain of definition of cosine. Okay, so cosine function looks like this. Okay, so it has the period like this. So we limit the domain from 0 to pi. So in this, if we limit from 0 to pi, then this is a strictly decreasing function. So we can define the inverse. So cosine from 0 to pi to negative 1 to 1. So its inverse is called arc cosine, and it maps this domain negative 1 to 1 to this range 0 to pi, and its functions should look like, so from 0 to pi, since it's so when x is 0, cosine 0 is 1. Wait a minute, no, not pi, sorry, should be it should be no. The domain of arc cosine is negative 1 to 1, so okay, sorry. So it should be negative 1 to positive 1. And when the angle is 0, the value of cosine is 1. So this is 1 and this is negative 1. And from 0 to pi. So wait a minute. So we have here, so it should have the value of here, and when so it should look like something like this. So the arc cosine should look like this. Okay, so that's the mirror image of along this axis. So we put to here, and this should come somewhere here. So that should be like this. Okay. And next, consider the inverse of tangent. Okay, so tangent is also a periodic function, and it looks like this. So this is x. So it has the basic period of multiples of pi, and 1, 2, 3, 4, 1, 2, 3, 4. So let's consider this interval. So tangent x in this interval looks like this. So it goes from negative infinity to positive infinity. And so if you limit to this domain, we can define its inverse. And it has, of course, it's a periodic function. So we have the same shape here and here. So here and here, and so on. So that's 2 pi, and so this should be pi and 3 pi half, and so on. So if we consider the entire real axis, then real numbers, then this is a periodic function and the inverse cannot be defined. If we limit the domain of this tangent function to this rate, to this interval, then we have we can define its inverse. So tangent is limited to this interval, negative pi half to pi half. So that maps to negative infinity to positive infinity. So this is a bijection. So if we define its inverse, it's called arctangent. And it's defined for all real numbers. And the range is between negative pi half to pi half. So its graph will look like this. So x, and so let's see. So that will be negative pi half, and 1, 2, 3, 4, 1, 2, 3, 4. So this is pi half. So it will look like this. So this has kind of, similar to S shape. S shape. It's called sigmoidal. So this is a very popular function used for neural networks as an activation function. Next and finally, we define hyperbolic functions. I just give you the definition first. So there are three functions which are very similar to trigonometric functions. So first, cosine h, hyperbolic cosine, is defined as this: e to the power of x plus e to the power of negative x divided by 2. And x is any real number. Okay, so this is called hyperbolic cosine. Hyperbolic cosine. Okay, and next, sine h, hyperbolic sine function, is defined as e to the power of x minus e to the power of negative x over 2. And x is any real number. And then, so this is hyperbolic sine, and as you might have guessed, next is hyperbolic tangent. And this is defined as sine hx over cosine hx. So that is, if you divide this by this, you have minus x over ex plus e minus x. Okay, so here are the definitions. Let's see their quantitative behavior by drawing their graphs. For example, for hyperbolic cosine, we have exponential of x plus exponential of negative x. And when we put x equal to 0, then it will be equal to 1. Right? So this will be 1, this will be 1, so 1 plus 1 is 2, and divided by 2 is 1. So the value of here is 1. And if we increase x to positive infinity, then this term will diverge and this term will converge to 0. So in total it will diverge to infinity, so it will be like this. And similar for x going to negative infinity. So in that case, this term here, this term will diverge to infinity, positive infinity, and this term will converge to negative, converge to 0. So in total, it will diverge exponentially to positive infinity. So this will be the qualitative picture of hyperbolic cosine function. And also, you should notice that this is symmetric around y-axis. So that is, this cosine h is an even function. So cosine h negative x is equal to cosine h x. So changing the sign doesn't change the value of the function. And next, let's consider sine hyperbolic, hyperbolic sine. So here we have a negative sign. So when we increase, when first let's put x equal to 0, then this will be 1, this will be 1, so it will be 0 in total. And x, if we move x towards positive infinity, then this will diverge and this will converge. So it will diverge to positive infinity. And if we decrease x to negative infinity, then this second term will diverge to infinity, but we have negative sign here. So it will diverge, in total, it will diverge to negative infinity. So after all, the graph of sine h will look like this. So at 0, it will have the value of 0. And it will diverge exponentially to positive infinity. And it will diverge to negative infinity as x decreases to negative infinity. So it will just diverge. So that's hyperbolic sine. And also you should notice that this is an odd function. So if we change the sign of x, then it will change the sign of the functional value. So we have negative sign here. Okay, then now consider tangent h. So tangent h, if you look at this, at x equal to 0, this is 0 obviously, because sine h is 0. And when we increase the value of x towards positive infinity, you should prove that this will converge to positive 1. So it will converge. And when you decrease the value of x to negative infinity, then this will converge to negative 1. And this is a monotone increasing function, so we have this behavior. So let's see, this is positive 1 and this is negative 1. So it will be like something like this. It will converge to 1 as x increases and converge to negative 1 as x decreases to negative infinity. Okay, actually when I talked about arctangent, I told you that it is used as an activation function for neural networks, but actually tangent h, hyperbolic tangent, is more popular than arctangent because this converges to 1 and negative 1, so that's easier to handle. Now positive 1, negative 1, that's very nice compared to positive pi half and negative pi half. Next, let's see one of the important equalities involving hyperbolic functions. So that is this. Cosine h squared x minus sine h squared x is equal to 1. Here, this cosine squared means this. Hyperbolic cosine x squared. And same for this. Sine hyperbolic x squared. So this is just like we write cos squared x rather than when we mean the square of cosine x and so on. So same here. Okay, so what does this mean? To consider this, first think about this identity. Cosine squared theta plus sine squared theta is equal to 1. So we know that this is the equation for a unit circle, right? So if we put x equal to cosine theta, y equal to sine theta, then we have x squared plus y squared is equal to 1. So this is the equation for the unit circle centered at origin. So unit circle. Okay, so let's do a similar thing for this equality involving hyperbolic functions. So let's put x equal to cosine h theta and y equal to sine theta. Okay, so we have x squared minus y squared is equal to 1. So what is this? So if you rearrange this equation a little bit, we have y squared is equal to x squared minus 1. So we have y is equal to plus minus square root of x squared minus 1. Okay, remember x is defined as cosine h theta. So as we've seen before, cosine theta has the minimum value at 1 here. Okay, so this x as defined by this is always greater than or equal to 1. Okay. So this is okay. So from this we can see y is indeed a real number. So no problem. So let's plot this function. So that will be like this. So at 1 we have square root of x squared minus 1, and negative sign will be this mirror image of the first one. So it will approach this line. So it will never go away from this line, but it gets closer and closer to this line. What's this line? That's y equal to x. And similarly, at this point, this line is y equal to negative x. So this curve gets closer and closer to this line. And this curve is called hyperbolic curve. Hyperbola. It's not parabola, it's hyperbola. Usually hyperbola comes in pair. So there is also a symmetric hyperbolic curve here. That is the mirror image of this mirror image of this curve. But in the present case, we have this restraint, x greater than or equal to 1, so we only consider this part. Okay, but anyway, this is hyperbola, therefore we call this function hyperbolic functions. And that's all for this chapter.